If you remember, for resistors in different configurations, we had an equivalent resistance, and we have the same idea for capacitors. So I'll first look at equivalent capacitance for capacitors in series. And this is where capacitors and resistors are very different. Because you might remember, for resistors in series, you can get the equivalent resistance by just adding up the individual resistance values. So in general, for a capacitor, the capacitance is equal to Q divided by the voltage across the capacitor. So then if we're looking at equivalent capacitance, I would have CEQ is equal to the charge divided by the equivalent voltage. Now, applying a subset of the loop rule, going from the bottom left corner, I'll call that A, to the top left corner, B, will actually give me the voltage across the capacitors. But instead of calling it a loop, I should really just call it a path. And before I do this, I want to actually take a look at which plates would be positive on the capacitors so that I can know how to add up the voltages across each one. So the EMF on the left-hand side sets up an electric field, and what it does then is the positive plate of the EMF will attract electrons from the left plate of C1. So the left plate of C1, because it's missing an electron, actually becomes positive, and so we're going to build up a positive Q on that plate. That electron ends up going through the EMF and down to A, and then that gets deposited on the left plate of C3. So we end up with negative Q on that left plate of C3. And the EMF isn't directly connected to the rest of the circuit. It doesn't do anything else. It actually continues to build up a positive charge on the left plate of C1 and a negative charge on the left plate of C3. But before I take a look at that, I want to actually explore what happens when the first electron has moved from the left plate of C1 to the left plate of C3. So if we look at C3, the left plate becomes negative because of the EMF. But then that negative plate is going to influence the opposite plate of C3, and it's going to repel an electron, which means that we would have a positive charge on that plate, and that electron gets pushed away and then gets deposited on C2. So we're going to end up with negative Q on the bottom plate of C2. That negative plate of C2 also repels an electron, making the opposite plate positive, so we get positive Q. And then, likewise, that electron that gets repelled gets pushed all the way over to C1, and we end up with a negative Q on the right plate of C1. So at this point, you could imagine that one electron has moved around. We've just somehow frozen time. We've taken a picture. I don't think we can see electrons in capacitors, but imagine that you have a really amazing camera and it's very high speed, and you've just closed the switch and we see one electron has moved. And that one electron has moved from C1 down to C3, and then without actually being connected through conductors, it has influenced the rest of the circuit. And there's this chain reaction of charging that goes on between the different capacitors. And this only applies for capacitors in series. But it's very important. Capacitors in series have the same charge. And what's more, if you were to replace the C1, C2, and C3 with a single equivalent capacitance, all you would see from the EMF's perspective would be the negative plate of C3 and the positive plate of C1. And those plates have negative Q and positive Q. So what it means is that actually the equivalent capacitance, or the charge on the equivalent capacitance, I'm just going to call that the equivalent charge, QEQ, is equal to Q1, which is equal to Q2, and is equal to Q3. So the individual capacitors all have the same charge when they're in series, and that's the same as the equivalent charge for the equivalent capacitance. Then, as time progresses and the electrons keep flowing, then we take one more electron from the left plate of C1 that deposits one more on the left of C3, which makes the right of C3 positive, and then that electron goes up to the bottom plate of C2, which makes the top plate positive, and then the right plate of C1 becomes negative, and this process continues. I'll do one more cycle. And this is what I mean by the chain reaction charging. The EMF, again, is only influencing the plates that it's directly attached to, but because the other plates are close by and they feel the effects, the electrons there get repelled by the excess charge on the left plate of C3, for instance, the rest of the capacitors all automatically adjust themselves when they're in series so that they have the same charge. All right, so now that I know which plates are positive and which plates are negative, I can actually look at that path and basically follow the loop rule and look at that path going from A to B. So starting at A, then I'm going from negative to positive on C3, so I have plus V3. Then I'm going across C2 from negative to positive, so I have plus V2. And then I'm going across V1, or C1, I guess, from negative to positive, so I also have V1. And this is the delta V across all of these. And I can also say that's equal to the equivalent voltage for an equivalent capacitor for all of these. And the reason I do that is because then I can substitute that in for the equivalent voltage to solve for the equivalent capacitance. So I have Q over V1 plus V2 plus V3, and the next step is to actually express the capacitance of each one in terms of Q and C. So from the general expression C is equal to Q over VC, that can give me that the voltage across any capacitor is equal to Q divided by the capacitance for any capacitor. So this means that V1 is equal to Q1 over C1, and V2 is Q2 over C2, etc. But because these capacitors are in series and Q1, Q2, and Q3 are all the same thing, they're all equal to Q, then I can just substitute that in too. Then I pull out the common Q on the denominator, and the Q's cancel out. Then the equivalent capacitance for these three capacitors in series is just 1 over C1 plus 1 over C2 plus 1 over C3, all to the power of negative 1. In general, for any number of capacitors in series, the equivalent capacitance is just the sum of the inverted capacitances, all to the power of negative 1. And I like this form of the equation because it's easy to plug this into my calculator. But you might also see it as 1 over the equivalent capacitance is equal to 1 over C1 plus 1 over C2 plus etc., depending on how many capacitors you actually have in series. And I don't always go through a lot of derivations in this course because I assume that you're getting that in the main course that you're taking, and I'm focusing on the highlights here. But in terms of capacitors in series, understanding this cascading effect in terms of the chain reaction or the cascading charging is important to really understand why capacitors in series have the same charge. So in this case, I felt like it was worthwhile. There are lots of problems where capacitors are connected in different ways, and understanding how capacitors charge in this way and how the charges move around from one capacitor to another is essential for being able to solve those problems.